Hello dear students, welcome to the fifth lecture of Introduction to Research Techniques, Applied Statistics. This is the outline of the course we are following, and we have reached now the point 1.2 on the probability density function. We have seen in the previous lecture that probability density functions, we are going to call them PDF as a nickname, are mathematical models. Models are by essence impossible to reach. They can be estimated, they can be looked from a certain distance, but we cannot get them absolutely, especially because they would require an infinite amount of measurements. We can, however, estimate them through statistics. Statistics indeed follow the path from reality to model by doing measurements, by looking at the histogram of the probability density as you have done, computing values like the average value. We can get closer to this model of the reality, which ultimately will be a mathematical model, which means with a function, with a mathematical function. Why so much effort to find this model? Because in the end, we want to predict. We want to say something about the future. You can imagine questions like, what is the probability to have rain next year for the agriculture? What is the probability that an epidemic rises? Or any kind of really important question you may want to ask. What is the probability that the price of the bread rises or lowers? These consequences are so important that sometimes you cannot afford to wait the events to come. You must beforehand know the probability of this event. So for that, you need the model of the reality. Once you have the model of the reality, you can extract from it a knowledge which is going to give you information about possible events. This model of the reality, in practice, is going to be a mathematical function like here. A mathematical function that works on values, for instance, the price of the bread, and here the probability. So we can see what is the probability that the price of the bread stay within this window, then it is the integral of this curve. So I hope I managed to convince you that knowing these probability density functions are one of the main goals of statistics. Not the goals, there are many interests. You remember surely that statistics is a toolkit, different tools, so different purposes. And one way we saw in the previous lecture to know this PDF is to understand the process. Last lecture, I had introduced you the process of throwing a dice, and we had seen that if the dice is balanced, well balanced, not perfectly, but well balanced, then a reasonable assumption, so a reasonable hypothesis, is that the probability is the same, so it is uniform. So the model, the mathematical model for this process will be a so-called uniform PDF, so a flat function between two values, exactly as we had expected in the previous lecture. The corresponding chapter in the Frodesen textbook is the 4.5. So here the x-axis is between a range A and B, while the y-axis has a single value, which is normal because it means that whatever the value of x is, there is the same probability, which is 1 divided by b minus a. Here we are going to find a consequence of the fact that the PDF is normalized. You remember that normalized means that the integral is the integral over the whole range is 1. In this case, it's really simple because it is a rectangle, which means the surface of this rectangle is 1. And when we write the equation 8 times length equal 1, we end up with the 8 here being simply this value. The advantage of having such a mathematical model is that also once the PDF is defined, so like mathematically defined, like here, then all the properties come very naturally. Which means that if we have a function, a mathematical function defined by that, so this is the mathematical model for the process of throwing a dice, then we can know, for instance, the average value and the variance. So the variance, it's somehow the standard deviation. Remember, there is just a square root between the two. How do we compute these expected value and variance? Using the definition I introduced in the previous lecture, which is that we compute the average with a sum. Now it is not a sum like when we sum over measurements, individual measurements, we sum over a continuous function. So we have a continuous integral here. And for those of you who know how to perform these mathematical operations, I invite you to do the exercise. It's pretty simple here, and you will see that the mean value and the variance have these values. In the case of throwing a dice, then the range is from 0 to 6, which means that the mean value is 3, while the standard deviation is about 1.7. With the dice, we have seen a very simple function, which is the uniform function. In practice, I should have said the discrete uniform. But for the sake of simplicity for this lecture, we are going to remain with continuous functions. Of course, not all processes are uniform. You can have different shapes, which are here just gathered in families like exponential ones, normal, triangular, and some with names you may have heard, like chi-square, Rayleigh, if you have done some physics, or even some distribution that you have never heard. There are in fact many different families of such PDF. So how can we determine this probability density function? we have seen first that the best step is to understand the process. So, like for the dice, if we can understand the process and make a reasonable hypothesis, then we go almost directly to the PDF. But in most cases, you will need to go from the probability density. So we are going to do this statistic process by doing measurements, making the histogram, and looking at the data. Always look at the data. This is really important. And then this tree of decision is going to help you know somehow what the PDF is. So it's not going to tell you the truth. It's just going to give you an idea, a direction. In the case of the dice, you can say, is the data discrete or continuous? It is discrete because the dice is only 1, 2, 3, 4, 5, 6, not 1.5, 2.8. Can you estimate the outcomes and probabilities? So in the case of a dice, we will say yes. But imagine that we say no, then okay, is the data that you can see, so we throw dice and we build data, is that symmetric or asymmetric? It's symmetric. Is that clustered around the central value? No, okay, it's uniform. So it's really crude, quite rough, but it's a really good step to start. I'm going now to introduce you a couple of PDF. These are like the main ones. It's like if you go to Afghanistan, you are going to visit Kabul, you are going to visit Herat, Mazar-e Sharif, and you will start with these cities. Even though there are many other cities, many other places to see, but this will be the main spot. And I will do the same here in the big country of the PDF. I will introduce you to the main ones. You have already seen one, the uniform with the dice. We are going to show you now another one called the binomial. So in binomial, you can see that, so B means 2. And in fact, a binomial PDF is a really simple process with only 2 outcomes. These outcomes can be success and failure. It can be anything. It can be, it goes on the right or it goes on the left. It goes up, it goes down. I win, I lose. Whatever process that you can split between 2 outcomes. And there are only 2 outcomes, which means that the probability of success is P, and then the probability of failure is naturally 1 minus P. So if you have 20% of success, you can only have 80% of failure, because there is no third option. In that case, the mathematical model for this kind of process is this function. So it looks a bit complex. Let's take some time to understand it. The probability to have a success, and a success, and a success, and a failure, mathematically is going to be the product of the probability for a success times the probability for a success 3 times the probability for a failure. And you can see that R being the number of success, you can see here exactly what I have written here. So we have R success and N minus R failures. So in practice, you can flip a coin. You flip a coin N times, and out of these N flips, you have R successes and N minus R failures. So this is pretty straightforward. What about this part here? I'm not going to dive much more than showing you this. If you have done some mathematics in the past, if you have done some combinatorial, this is a mathematical notation. So if you have 3 with this notation, it means 1 times 2 times 3. If you have 4, it's 1 times 2 times 3 times 4. And the reason why there is this coefficient is because the order does not matter. So here, if I give you n equal 5, so 5 trials and 2 success, you can have success, success, and then failure, or failure, then success, or any mixed value. So the combinatory doesn't matter. They are all accepted. And this expansion of the expansion of the number of cases that you accept because of the combinatoric is expressed by this coefficient. If you want more details about this function, I invite you to look at the chapter 4.1 of the Froedesen textbook. The binomial PDF is a PDF that describes any kind of process with 2 outcomes. And when you really think about that, it's really general. Because if you have politics, even if you have 10 parties, then basically if you look at one party, is you win or you lose. It's the same for sports. It's the same for sampling. It's a really general function. And this is the mathematical model that describes this kind of processes. So it's really, that's why I wanted it to be the first. It describes a simple process in a really powerful way. We call it also the Bernoulli. So Bernoulli is a mathematician from Switzerland, from a very famous family of scientists. Especially if you do hydrodynamics, you may have heard also about the Bernoulli formula. One important property to keep in mind about the binomial process is that the shape is going to change depending on the parameters. So n and p, which are here, are parameters. These are not the random variables. The random variable is the number of success. So you flip a coin 10 times. How many times are you going to have a given side? This is the random variable. This is r. So the x-axis is going to be r. And depending on the n and p, on the parameters, the shape is going to be different. I give you here some example. So here, if we flip 20 times the coin, or if we flip 5 times, you can see that the shape is not the same. Here, the shape goes to the left, and we can see that it's almost close to being an exponential, while here it goes to the right and it starts to be like a mountain, like a Gaussian. We'll see that later. And we can, of course, compute the expected value and the variance using the same formula as we had before. And we have this extremely simple and sympathetic result about the mean value and the variance. So in practice, if you flip a coin where the probability is to have 50% on one side, 50% on the other side, if you flip 10 times, in average, you will have 5 on one side, and the standard deviation is going to be about 1.6. So 1.6 will say 2. Remember, it's the mean value plus or minus the standard deviation. So we should expect between 3 and 8 on one side. So if you flip a coin 10 times and you get 8 on one side, it's not a miracle, it's statistics. The next PDF I'm going to introduce you is the so-called exponential. Imagine that you live in a country with earthquakes and you measure the time between two earthquakes. So every day, every month, every week, somehow you have an earthquake and you measure the interval between each of these earthquakes, the consecutive time. This interval here is the random variable we are interested in. And this kind of difference is described mathematically by an exponential function. X here is the value of the interval, and beta is a parameter. So beta here belongs to the Greek alphabet. So you remember we use a lot the Greek alphabet. And here we have one random variable and one parameter. The shape of this exponential PDF looks like that. So it's falling down. And depending on the value of the parameter, the shape can differ. So you can see that we can have something really steep, or on the contrary, something quite flat. We can also compute the mean value and the variance using the same definitions as before. And we get these really simple results that the mean value basically is the parameter. And the variance is beta square, which means that the standard deviation is beta as well. So you can see the exponential PDF, despite being may look complex, is in fact pretty simple. How do we interpret this? It's basically if you are here and you ask, okay, when is the next earthquake? You don't know when it is, but you know that what is the probability that I wait more than, for instance, 3 hours. And then when you have this mathematical model, it will tell you the probability is the integral. So it's going to be this tiny integral. So the probability is going to be smaller and smaller as the time goes on. So what is the probability that you have an earthquake in the next 30 minutes? It's going to be too small, and the more and more you wait, the more and more an earthquake gets probable. The last PDF I'm going to introduce you is the so-called Gaussian or normal PDF. It's named Gaussian from a mathematician, a German mathematician called Gauss. And whatever you may have studied, if you have touched some mathematics, you must have heard about a Gauss theorem in whatever realm. This man was, we can honestly say, a real genius in his time of mathematics. And the Gauss function is not the only thing that he has worked on. He has not, of course, been the only one to work on that, especially because this function is probably the most important PDF in probability and statistics. The mathematical model is this one. So this is the function. You can see it is in two parts. You have here a coefficient and then an exponential. The random variable here is x, and we have two parameters. One parameter is mu, so the mean value, and the other one is sigma, it's the standard deviation. the Gauss PDF looks like a mountain. See, like we say also a bell curve. The mean value is the mu, as given in the definition, and the standard deviation is sigma. One reason why this Gauss PDF is so important is the central limit theorem. And this is, without any doubt, the most important theorem in probability. If you think that statistics is complex, if this theorem did not exist, it would be even more complex. This theorem really often makes our life much simpler and easier. So what does this theorem say? Imagine you have a set of random variables, like you measure the cardamom length for different classmates. So one from Zora, one from Zoal, one from Amina. Each of these follow a different PDF with each time a different mean value, different standard deviation. And we consider the sum of these random variables. What is going to be the PDF of the sum? So they all have a different PDF. No, it's not necessarily the same. We make the sum. The PDF of the sum is going to be a Gaussian. And that's really cool, because it means that if you have different things that you don't really know, you just need to sum them, and you know for sure that the sum is going to follow a Gaussian. This is valid only if n is large enough. So typically large enough is, 10. As long as you sum 10 random variables, you have a Gaussian PDF. The mean value of this PDF is going to be the sum of the mean value, and the variance is going to be the sum of the variances. So you can see also why we defined the variance and the standard deviation, even though the difference is really ridiculous. It's just a square root. It's because here the variance is the sum of the variances, something called a geometric mean. And I really want to emphasize that the beauty of this theorem is that you can start with different random variables that arise from different PDF, so really different shapes. If you sum them, you end with a Gaussian. And this Gaussian has wonderful properties in mathematics. You can derive, you can integral, it's really well known, there are tables about its values, so you can start with things that you don't know how to describe, you sum them, and you get something that is easy and well known. And now I want to go back to the first lecture where I told you that when we define the average is not, in statistics, it's not the most interesting definition. We may be more interested by the median. So why do we still care about an average? Because it's a sum. You remember? And what happens if it is a sum? It means that the shape of the average is a Gaussian. The PDF of the mean value, if we compute several times a mean value, it's going to be a Gaussian. And not just for the mean value. You remember the standard deviation? It's a sum. Oh no, there is a square root. Okay, we get rid of the square roots by defining the variance. You see, that's why we wanted to have a variance. Even though it's hard to understand and, okay, why do we need that? Having a variance is really cool because a variance is a sum. And the mean value is a sum, which means that the PDF of these estimators are known. It's a Gaussian. So we have been through quite briefly the question of probability density function, and I really want you to keep in mind these few examples: the uniform, the binomial, the exponential, and the Gaussian. I will end now with the chapter 1.3 and population and sample. When we say population, ordinarily we think about human population, the Chinese population, the Japanese population. But in statistics, population is more general. A population is not necessarily a group of humans. It can be a group of animals. It can be a group of cities, like all the villages in Badakhshan. It can be also a group of events, like all the arrivals of the buses. And this is this population that we are interested in statistics. So for instance, we are interested by all the villages in Afghanistan, for instance. Because we are interested in all the villages does not mean that we are able to investigate all these villages, because sometimes we cannot access them, we don't have enough time or people to go in. So we need to do a sample. A sample means we are going to take just an example. Of course, the choice of this sample is extremely important in order not to bias this sampling. And there is in fact a whole question, a whole chapter dedicated to this sampling. So this process is called sampling. It can be, for instance, just one village, or maybe just a street, or your family. And once we have this sample, we can measure it, because we know that we can go in this village, we can, for instance, measure the people, count the houses, and so we can start to describe random variables. For instance, how many children per family? What is the average income? And now we can start to describe this small sample. But remember, what we are interested in is not the sample, it's the population. So we need here to do so-called inference. Inference means that we have an assumption to do on the population from the sample. For instance, we are going to say this village that I see is a good representation of the village in all Afghanistan, for instance. So by doing that, I am able to extrapolate what I have seen here to know more about the whole population. So this whole population has a PDF that we cannot know. Okay, we cannot access it, but we need to estimate that. And I wrote that in red because it's a real word, it's a real technical word, it's estimation. And to go from here to here, we need estimators. So the properties of the sample are measured, while the properties of the population, which are unknown, must be estimated. So these estimators, basically it's like when you fly an arrow to a target. So you take the bow, you aim at the target, and what you want is you want the arrow to fly straight into the center. And it's the same for the estimators, except that to say direct in the targets, we have some words like consistency, unbiasedness, minimum variance, efficiency, and sufficiency. If you go on the chapter 8 of the Froedtert textbook, you will have a clear description of each of these properties. But in practice, what these different properties mean is that when you measure something here and you extrapolate it to the population, this extrapolation must converge in a precise and exact way. So if you aim at the right value of the population and you compute it with the sample, you should go straight to this value and not diverge. And when you set these values, you set these, not these values, these properties, you see that the mean value and the variance, they must be defined by this equation. So these equations here are a consequence of having an estimator that is consistent and biased, etc. So if you ask where does that come from, it comes from the fact that we need an estimator that targets the population. And this is where you need to be really careful about some formula that you use. If you look at Excel, you have probably noticed that Excel offers two ways to compute the standard deviation. There is the formula STDEV, but it's kind of tricky because you can have stdev.p or stdev.s. PS population sample. The population one is going to use this formula, while the sample one is going to use this one. The difference between this one and this one is this n-1, and here it's n. The idea is that this value, when n, so small n here is much, much smaller than this one. So for instance, this is for the whole Afghanistan, you cannot get it. This is just for bad action. But if the estimator is good, so when this number converges to n, this value should converge to that. And because here we need to measure the mean value also from the same sample, one consequence is that we cannot use the same normalization factor. Keep that in mind, that there are two ways to measure the standard deviation. In practice, the difference is small because it's just n-1. So if n starts to be large, the difference gets really small. But if you have different standard deviation, you compute different standard deviation, and you don't have the same value, then think about that. Quite a long lecture. Huh? And for that, I give you an assignment. It's just for the next 2 weeks, so that you have time to read this lecture, digest, wonder, why did I choose statistics, and then read again and start to understand. Take your time. Statistics is complex because the world is complex. You remember Leila with the goat and the cardamom in the bazaar? Okay, she's on the way back home. You had advised her to buy a bag of cardamom on the last assignment, and she's back home now. We are going to meet now Roya. Roya is a bit older than Leila. She's Leila's cousin. She does not live in the village. She lives in the city, because they thought it would be better for their education, for a friend. But today, Roya is getting bored. Because of the situation, she meets less friends, and thinks, nobody wants to call me. and she's a bit annoyed because she thinks that she's alone. I would like to show you that, as surprisingly as it can be, statistics may help Roya to feel better. And this is going to be your assignment. This is what you're going to do. You are going to get your phone, if you have a phone. Otherwise, working group, take the data from someone else. You go to your phone and you get the 20 last call that you had. For each call that you received, there is, of course, an hour, a date and an hour. I want you then to extract the duration between each call. This is going to be the random variable. So we are going to do now descriptive statistics. So you make the measurements. Each call, what is the duration between two consecutive calls? So from 10:30 to 11, 30 minutes. And then you see here 10 minutes, here 23 minutes, so on and so forth. Once you add that, build the histogram, build the probability density. Before, which PDF do you think it's going to follow? Which mathematical model do you think that this random variable is going to follow and why? I want you then to build the distribution probability and compare what you see with your expectation. Then, given this histogram you have, on which duration there is a 90% chance that you receive a call. So what I mean by that, maybe your last call was 1 hour, 2 hours. After how much time there is a 90% chance to receive a call. So if you say, for instance, okay, the last call I received was 3 hours ago, and now there is a 90% chance that I receive a call soon. The consequence is, nobody has called me for 3 hours, but it's going to come soon, okay? There is a statistical certainty that is going to come, and the size of this certainty is 90%. So then, which advice would you give to Roya when she thinks that nobody wants to talk with her? The second part of this assignment is going to focus on the central limit theorem. So you had these measurements with the phone logs, the duration between calls. I want you to find 5 other classmates. And I want you in Excel to align your tables. So first classmate, second classmate, so on, okay. So you're going to have 5 columns. I want you to sum 2 and make the histogram of the sum. Then I want you to sum 3 and make the histogram on the sum. Do the same for 4, do the same for 5. Each time build the histogram and explain me what you see. So it's a long and complex assignment, so I strongly invite you to collaborate, help each other, ask questions if you need, and good luck. For the next week, we're going to have a special session with question and answers. We are going to look at the previous lectures and the previous assignments. Take care of you and goodbye. Thank you very much.